One of the major goals in calculus is to find this exact area under this curve. So what do we mean by that? Well, given a function, we'll assume it's above the x-axis for now, but given a function, block off some interval on the x-axis. We'll call it a to b. One large goal in calculus is to find this exact area between a and b, and then also between the function and the x-axis. Let's call it a. That is a major goal in calculus, finding a. And we'll see we can use limits to find a exactly. But before that, we need to build it up a little and build up what we're going to do. What we're going to do is approximate this area. And then we'll use a limit to infinity to find the exact area. But how are we going to approximate it so that we can get the exact area in the limit? Well, we're going to use rectangles. So we're going to take this interval a to b, and let's just say we divide it up into a certain number of pieces. So here we've divided the interval a to b into 4 equal pieces. We'll assume they're equal for simplicity. So divide a to b into 4 pieces and use that to form these vertical lines that divide our area into 4 pieces. Now, right here, we can't find the areas of these pieces. So what we're going to do is approximate it by using areas we know. We know areas of rectangles. So let's just use where the function intersects the vertical line as a corner for a rectangle. So we divided the interval into 4 pieces, and we used that to find 4 rectangles. Now, given a function and an interval and a number of rectangles, we can add these areas of rectangles up. But you'll notice we wanted this exact area. But here, if we add these rectangles areas up, we're not going to get the exact area because we have these 4 wedge-shaped pieces that are not contributing to the area, or that are not contributing to the rectangles, but are contributing to the area. So right here, if we do this, this would be an approximation. But what would happen if we divided it into more than just 4 rectangles? What if we divided it up, I don't know, into however many I'm about to make? Looks like 8. If we divided our interval into 8 pieces and used them to form rectangles, well, what would that look like? That would look like those 8 rectangles. Well, let's fill in their areas. That'll give us that area, plus that area, plus that area, that area, that area, that area, that area, and that area. Now, if we divide it into more rectangles, there is still an error piece. In this case, there are 8 wedges. Here there were 4. But one large result in math is that if you combine all of these 8 wedges, and you'll get a certain area, you'll get a piece of this area not counted if you add these 8 wedges together. If you add these 4 wedges together, you will get a piece of the area not counted. But a large result in math is that with this larger division, let's say 8 rectangles, these 8 wedges add to less area than these 4 wedges. In other words, as you divide your interval up more and create more rectangles, the error term, the ERROR term, which is these 8 wedges versus these 4 wedges, the error term gets smaller as you use more rectangles. So here we have a certain error given by those 4 wedges. Here we have a certain error given by these 8 wedges. this error is less than this error. And if you use even more rectangles, say you use 1,000 rectangles, the error there will be less than the error for 8 rectangles. In other words, as you let the number of rectangles get large, this difference between the rectangle area and the actual area gets small. And in fact, as you let the number of rectangles go to infinity, the difference between the rectangle approximation and the actual area goes to 0. In other words, as the number of rectangles goes to infinity, this approximation becomes exact. So let's do some of those computations. But let's formalize this a little bit more first. So let's take this same type of function that looks like this. And let's see what kind of rectangles we can use. And let's introduce some notation. So the first observation you make, let's just say we're going to add areas of 4 rectangles. So observe. So we have one function, let's make it the same function. A to B, we want that area. And let's do one right next to it. Same function. Let's do A to B. So now, the first thing you'll observe, let's just say we're dividing this into 4 rectangles. Well, this is the same diagram we had before. We divide the interval into 4 pieces, and then we use these points to form rectangles. And that's what we get. But there are actually 2 different choices of rectangles you could use. Where? Well, let's do the same thing over here. Divide the interval into 4 pieces. Notice how we formed these rectangles. Well, let's not notice how we formed these rectangles until I form these. We could have also done this. And formed rectangles like that. And we get areas, or we'd get areas of rectangles like this. Now, first observation you might make with this is that these look like completely different approximations. Because in this one, the area of the rectangles is much less, well, not much less, it is less than the exact area we want. Here, if we add the areas of the rectangles, we will get more than the area we want. So let's call these 2 approximations different notation. Here we used 4 rectangles, and let's look at how we formed them. We started up here and we went over. We started up here and we went over. Started up here and went over. Started up there and went over. How did we form these? Well, we started up here. Well, let's start down here actually. We started down here and went over. We started over here and went over. We started here and we went over. We started there and went over. In other words, what we did when forming a rectangle, let's look at the base of the rectangle. There's this point and this point. When we formed the rectangle here, we used this x value. We used this x value to define the top side of the rectangle. We used the leftmost of those 2 endpoints. And because of that, we're going to call this approximation L4. Over here, when we formed the first rectangle, well, again, we have 2 endpoints we could have chosen. But here, when we formed the top side of the rectangle, we used the rightmost endpoint. Here we used the leftmost endpoint. Here we use the rightmost endpoint. And we'll call this approximation R4. So R is for the right endpoints, 4 is because it's 4 rectangles. L is for the left endpoints, 4 is because it's 4 rectangles. So let's just make this a little more formal. L4 is the combined, let's make this, I'm not going to make this a definition. L4 is the combined area of the rectangles, well, maybe I'll say of the 4 rectangles, L4 is the combined area of the 4 rectangles found using left endpoints. And similarly, R4 is the combined area, I'm just going to write a line to mean the same sentence, of the 4 rectangles found using right endpoints. So for the first rectangle, we used the left endpoint to define the top. For the second one, we used the right endpoint to define the top. And while combining this with the observation we made before, if we let this number go to infinity, we said that that would give the exact area. If we let this number go to infinity, we might also get the exact, well, we do also get the same area. That's actually a large result in math. So I'll call it a theorem. Well, before theorem, if we let n equal the number of rectangles used in the approximation, that's what that says. So if we let n, well, let's just say not if we, sorry, I should make this its own sentence. Let n equal the number of rectangles used in the approximation theorem. What we said a few minutes ago was that if you let the number of rectangles go to infinity, then you'll get the exact area. So one part of the theorem is that this equals A, the initial area we wanted. An important result in math is that you could have also used the right endpoints. So you could use left endpoints, or you could use right endpoints. Either way, if you let the number of rectangles go to infinity, the approximation becomes exact, with right endpoints or with left endpoints. So now, before seeing exactly how that computation works, let's do a couple examples where we just add areas of a small number of rectangles. And then we'll generalize that to the entire area. So let's do this example. And this will be how these examples are phrased for the most part. Approximate the area under the curve. Let's give a curve. F of x equals x squared plus 3 on the interval 1 to 3 using A, B, C, D. So first using 2 rectangles. Second using 4 rectangles. Third we'll use 8 rectangles, and finally we'll use 3 rectangles. Now, when I say approximate the area under the curve, you could use either right or left endpoints. So there might be some where I ask for both approximations. If I don't ask for both approximations, you can choose only one of the approximations. In this example, I will do both approximations for all 4 examples for illustrative purposes. So let's first look at this function. This function looks like this. We're looking at the interval 1 to 3. There's 1. There's 3. We want this area. For part A, we want to divide it into 2 rectangles. So let's do that. There's 1 rectangle. There's the other rectangle. Let's also make the other rectangles for the other approximation. There's 1. I should probably make 1 look like 1 looks over there. So 1. There's 3. We're going to divide that into 2 pieces, and we're going to form rectangles using the right endpoints over here. So on this board, we use the left endpoints. On this board, we use the right endpoints. Now, the first thing we need is this x value. So that x value is directly between 1 and 3. When we say approximate using rectangles, we will assume all of the rectangles have equal base. So here we want 2 rectangles of equal base. We have the interval 1 to 3, so all we need is their midpoint, which is 2. And similarly over there, that's a 2. So now we just need to add areas of rectangles. So here we have L2 equals, well, how can we find this? The first thing we did when we set these up was ensure that the 2 bases were the same. Well, let's write that out, or let's write out the areas of the 2 rectangles separately and then make an observation. The area of the first rectangle, base times width. The base has length 1. So 1 times what? Times the height. Well, what's the height of the rectangle? The height of the rectangle is that line. That's a y-axis point. It's a y value. It is the y value that occurs when x equals 1. The y value that occurs when x equals 1 is what? 1 squared plus 3. So that ordered pair, 1, 4. The y value is height 4. So the first rectangle has area 1 times 4. The second rectangle, the base is still 1. Well, it's also 1, I should say. And the height is given by this value. The height is given by that y value. It is the y value that occurs when x equals 2. The y value that occurs when x equals 2 is what? 4 plus 3. Substitute into the function. You get 4 plus 3. 4 plus 3 is 7. So we have 1 times 4 times 1 plus 7. We have 1 times 4 plus 1 times 7. And that equals what? That equals 11. But let's make one observation before jumping to 11. It might not make that much sense in this example. It'll make more sense in the next 3, but I'll use this example to illustrate. Both of these terms have a 1. So you can actually factor out that 1. And you get 1 times 11, which is 11. But how is that factoring out reflected in the actual problem we were doing? Well, both of these sides are length 1. So you can factor that out when you're doing the area computation, because all you're doing is adding length times width. If the one side is always the same, you can factor that out. So let's look at this next one. So here we have, not A, we have R2. So here we have R2. And let's make that observation about factoring out the one side, since we set it up so that the bottom would always be the same, the base would always be the same. So here we have length 1. The bases of the rectangles are all 1. And now we just need the heights of the rectangles. Well, what's the height of the first rectangle? It's not determined over here. It's determined by the right endpoint. The first rectangle has this height. This height is the y value that occurs when x equals 2. So 7. X equals 2 would give us 2 squared plus 3, 4 plus 3, which is 7. The next rectangle has height given by this y value. The y value that occurs when x equals 3. When x equals 3, you get what? 9 plus 3, which is 12. So using right endpoints, our approximation with 2 rectangles is 19. 12 plus 7 times 1. Let's look at 4 rectangles. I'm going to erase the entire board for this one and the next one, and probably the next one. So what happens if we use 4 rectangles? We're still on the interval 1 to 3. Over here we'll do L4. Over here we'll do R4. Again, in your work, if you're just asked to do an approximation, all you have to do is one of these two. Unless I say to do both. Then you have to do both of them if you want full credit. So here, we're going to divide the interval into 4 pieces for part B. And this is still, I'm going to call it f of x this time. So we're going to divide it into 4 pieces now. Well, there are 4 pieces. Now what we need are these x values on the x-axis. I find in these that the hardest part is actually finding the x-axis values. Because once you have the x-axis values, all you need to do are a bunch of length times widths. Now how do we find the x-axis values? Well, this is from 1 to 3. To divide it into 4 pieces, we first divided it in half. The number between 1 and 3 is 2. Then we also divided this in half. The number between 1 and 2 is 1.5. The number between immediately between 2 and 3 is 2.5. And for algebra purposes, we'll call 1.5 3 halves, we'll call 2.5 5 halves. And similarly over here. We have 2, then we have 3 halves between 1 and 2, and 5 halves over there. Well, now we have this set up, we can form our rectangles. So we formed our rectangles like this. And over here we form them using the right endpoints. Using the right endpoints over here. And using the right endpoints up here. And now all we have to do is add areas together. So our first observation is that the base of all of these rectangles is 1/2. So we'll write a half, and then we'll add all of the heights together. The first height is given by that y value. And here, I'm not going to write out that exact y value. I'm going to use the function to write the y value. I'm also going to write this a little smaller. L4 equals a half times. Well, a half times what? Well, the first height is given by the function at 1. So let's call it f of 1. The second height is given by the function at 3 halves. So let's call it f of 3 halves. I guess I won't be able to fit R4 there. The next one is given by the function at 2. So let's call that f of 2. Well, not let's call it. It is called f of 2. The last rectangle's height is given by f at 5 halves. So you can see the way we've set this up, the way we've set our rectangles up, is so that we will have an equation like this, where we can factor out the one side, and then all we have to do is do for the left endpoints f of 1, f of 3 halves, f of 2, f of 5 halves. Because we're using the left endpoints. And let's figure out what this actual number is. F of 1 is 4. F of 3 halves is what? 9/4 plus 3? 9/4 plus 3. Let's just write 9/4 plus 3. F of 2 is 4 plus 3, so that's 7. F of 5 halves, 25/4. 25/4 plus 3. So let's just write that as 25/4 plus 3. And let's add all these numbers up. You could do them in order. I think it's easier to not do that. 4 plus 3 plus 7 plus 3 is 17, because it's what, 10 plus 7? 17. 9/4 and 25/4 makes 34/4. 34/4 does not equal 17/4. 34/4 equals 17 halves. Now, how can you do this? Well, I would add these up in the middle next. So this is, what, 34 halves plus 17 halves? I'm going to go over here. So the inside here, 34 halves and 17 halves. 34 and 17 make 51. So for the left approximation, with 4 rectangles, we got 51/4. So this all goes with the left approximation. Now let's do the right approximation. R4, I'm probably not going to fit it on this board. I guess I'm going to erase. What do I want to erase? Well, I'm going to erase everything except the first line for now, because I want to keep that on the board. So this goes with the left approximation. That equals, with work, 51/4. Let's now do the right approximation. And when I'm saying right, I don't mean correct, with the right endpoint approximation. And we're using 4 rectangles. So let's do the same thing we did, but with the right endpoints. The base is still a half for each rectangle. Well, and what do we do to form these rectangles? Well, instead of using the left endpoints, we're going to use the right endpoints. So for the first rectangle, the right endpoint is 3 halves, or is at x equals 3 halves. So we get f of 3 halves. So R4 equals a half, which is all the bases, times f. The first one occurs at 3 halves. The next rectangle base occurs at 2. So the height is given by the function at 2. The next rectangle base occurs at x equals 5 halves. Or not base, the next rectangle height occurs at x equals 5 halves. So the height of the rectangle is given by f of 5 halves. And then the height of the last rectangle is given by the function at 3. So that's just f of 3. And let's go through this computation before making an observation. Equals a half. F of 3 halves, well, we already figured out f of 3 halves over there, and I erased it. It's what, 9/4 plus 3. F of 2 was 7. F of 5 halves was 25/4 plus 3. And f of 3 is 9 plus 3, which is 12. And we combine all these numbers. What do we get? 7 and 3 make 10. 12 and 3 make 15. 10 and 15 make 25. 9/4 and 25/4 again make that what? 34/4, which is 17 halves. Then we add these together. 25 is 50 halves. 50 halves plus 17 halves gives you 67 halves. And then that times another half is 67/4. So the right endpoint approximation gives us 67/4. The left approximation gives us 51/4. Now, let's look at these two equations. Just look at the L4 and the R4 equations. Both of them, the base of the rectangle was a half. Over here, we use the left endpoints to find the heights. And you can see that all we did was the function at the first one, plus the function at the second one, plus the function at the third one, plus the function at the fourth one to form the fourth rectangle. Over here, what we did instead, we jumped over this first one, and to find the heights, we just did f at this number, 3 halves, f at 2, f at 5 halves, and f at 3, and we added them all together. And using that observation will help us with part C. It'll help make part C easier. So part C says use 8 rectangles. And in part C with 8 rectangles, I'm not going to require that you find the actual number, because I'm not going to do that. That's not worth doing. So let's look at 8 rectangles. And maybe I should make this graph go out a little more for 8 rectangles. So there's our function. Let's call it f. I could call it f of x, but I'll just call it f. We want to divide this interval into 8 pieces. So first, we'll divide it in half. That's at 2. Then we'll divide this in half. 1 1/2. Divide this in half. Gives you 5/4. The way I like to see that is with like literal quarters. $1.50 is 6/4. $1 is 4/4. So right between them is 5/4. And similarly, between 1 1/2 and 2 is 7/4. Between 2 and 3 is 5 halves. Between 2 and 2 1/2 is 2 1/4. Between 2 1/2 and 3 is 2 3/4. And for algebra purposes, we will use the improper fractions. Now we use this to form the rectangles. I'll draw out the left endpoints. They look like this. And now we need the left approximation with 8 rectangles. Now, the first thing we'll notice is that the base is length 1/4. The base is length 1/4. Well, let's go from there. Well, actually, before going from there, let's make 2 observations about this. First, this being 1/4, you could get that from looking at this piece. You could have also gotten it without a diagram. because in this example, we're taking the interval 1 to 3, and we're dividing it into 8 pieces. Well, if we're dividing it into 8 equal pieces, which we are, well, the interval 1 to 3 has length 2. The interval from 1 to 3 has length 2. That's 3 minus 1. We're dividing that into 8 pieces. So we get 2/8, which is a quarter. That right there would tell us the length of the side. Another observation we'll make is on these x-axis values. So sometimes they're difficult to find. Once you find one of them, the first one I like to find, you can actually use that to find the rest. So here we're dividing into 8 pieces. So first, I divided it in half. Then I divided it in half again. Then I divided it in half again. And that gave us that the next x value was 1 1/4. Well, you could have also arrived at that 1 1/4 with this observation. The 3 minus 1 over 8 equaling, and how we got to that 1/4 before. You could use that observation to find these x values. So we knew from the work I erased that each interval had length 1/4. Well, if each interval has length 1/4 and you're starting at 1, well then you go over a quarter. You go from 1 to 1 1/4. You go from 4 quarters to 5 quarters. Well, look what happens after that. 4 quarters to 5 quarters. 5 quarters to 6 quarters. 6 quarters to 7 quarters. 8 quarters. 9 quarters. 10 quarters is 5 halves. 11 quarters and 12 quarters. So you could count out these x values like that as well. But here we want the approximations, and we want the left endpoints, which will be these endpoints, and we just have to add all them up. F of 1 plus f of 5 quarters plus f of 3 halves plus f of 7 quarters plus f of 2 plus f of 9 quarters plus f of 5 halves plus f of 11 quarters. And then you can find those numbers if you want. I'm not going to require that you find that many numbers. We start at 1, a quarter, 3 halves, 7 quarters, 2, 9 quarters, 5 halves, and 11 quarters. Well, and similarly, with the right endpoints, we're going to use the right endpoints, which would be those numbers. So R8 equals a quarter. This is part C. R8 is a quarter. Instead of starting at 1, we'll start at 5 quarters. So f of 5 quarters plus f of 6 quarters plus f of 7 quarters plus f of 8 quarters, 9 quarters, 10 quarters, 11 quarters, not 11 halves, 11 quarters. And then f of 12 quarters, which is 3. And if you want, you can find those numbers. But I'll just set them up for this one. I would never ask you to find 8 numbers like that. Maybe I would. But notice how those two lines were basically the same, except for the starting points for the 8 rectangles. Now part D of this said to do this with 3 rectangles. So let's do this with 3 rectangles. I find the one with 3 rectangles harder than the one with 8 rectangles. So 3 rectangles. And I find it harder because I find that finding the x-axis values is requires more thinking. So we have this. We want to divide it into 3 pieces. Well, dividing it in 8, you could do that by dividing in half, then dividing in half, and then dividing in half. But dividing into 3, you can't do that. So we're dividing that into 3 pieces. So to start, I'm going to do it the other way. Or do it, not the other way. Before, when finding the x-axis values, I divide it in half, then divide it in half. We can't do that, so instead, I'm going to look at the length of the intervals. So this is an interval of length 2. It's 3 minus 1. We're dividing that into 3 pieces. So the base for all of our rectangles is going to be 2/3. Well, if the base is 2/3, we need this x value, and we need this x value. Base is 2/3, we start at 1. We start at 1. We go over 2/3. 1 is 3/3. 3/3 and 2 more thirds is 5/3. 5/3 and 2 more thirds is 7/3. 7/3 and 2 more thirds gives us 9/3. And once we have this, we can form the rectangles and add the areas. You don't necessarily have to draw the diagram. I like drawing the diagram sometimes. So 2/3. We want the left endpoint, so we're going to use these values. So we have f of 1 plus f of 5/3 plus f of 7/3. And this function is given by those values. Well, so let's find these numbers. Equals 2/3. F of 1 is what? F of 1 is 4. F of 5/3 is 25/9 plus 3. So let's write that out. 25/9 plus 3. F of 7/3 is 49/9 plus 3. Well, now we just have to add these numbers up. So it equals 2/3. 4, 3, and 3 make 10. 25 and 49 make what? 74/9. 25 and 49, yeah, 74/9. This equals 10 plus 74/9. Well, 10 is 90/9. 90 plus 74 is what? 164? Yeah, 164. And then we just have to multiply the bottom, gives us 27. The top gives us what? 2 times 164 is 328. 328 over 27. Well, that's great. Let's do the right approximation now, the right endpoint approximation now. And I have an eraser, which makes doing the next approximation much easier. I didn't even have to erase everything I erased, but I did. So here we want R3. The only difference is we're going to use these endpoints now. So instead of f of, I guess I had to erase most of it. Instead of f of 1, f of 5/3, and f of 7/3, we're going to do f of 5/3 plus f of 7/3 plus f of 3. Well, now we just have to add those numbers up. We found some of them before, but well, I'll just write them all out now. F of 5/3 was what? 25/9 plus 3 plus 49/9 plus 3. F of 3 is 12. 3, 3, and 12 make 18. The other things make 74/9 again. Do they? Yeah. 18 is what over 9? 18 times 9 is 180 minus 18, which is 162. 18 times 9, 180 minus 18. 162 plus 74 gives you what? 236? No, that can't give 236. That reduces. Oh no, that doesn't reduce. What am I talking about? That gives 236 over 9. And then 2 times 236 is what? 472. And that doesn't reduce. Why does this not reduce? Well, it doesn't reduce because this doesn't reduce. 2 and 9 don't reduce, 2 and 3 don't reduce, 236 and 3 don't, 236 and 9 don't. Because that adds to 11. 2, 3, and 6. So here we have different approximations. Let's make one final observation about these approximations. In every example we did so far, the right-hand approximation gave us... Well, no, let's start with the left. In every approximation we did, the left endpoint approximation gave us an under approximation. So let's write that as a remark. Remark. In the approximations thus far, FAR, the left, how should I write that? Where's my eraser? In the approximations thus far, this is a terrible sentence. I'm just going to change the sentence, sorry. Remark. Thus far, left hand approximations. God, I can't write FT right now. L-E-F-T. There. Left hand approximations give an under approximation. And the right hand approximations gave an over approximation. And right hand approximations gave over approximations. This is not always the case. Let's look at this example. This is not always the case. If we just take this interval and use a left-hand approximation, let's use 4 rectangles. If we use left-hand approximation here, we would get those 4 rectangles. And notice if we added them all up, it would give us more than the area under the curve. So here, the left-hand approximation, I need an abbreviation for a left-hand approximation. LHA. Here, the left-hand approximation is an over approximation, and in this case, the right-hand approximation would also be an under approximation. The right-hand approximation with 4 rectangles would look like this. That last one's kind of poorly drawn. But the right-hand approximation would be an under approximation. I'll just say right hand is an under approximation. So in those examples before, the left hand gave an under approximation and the right hand gave an over approximation. In these examples here, the left hand approximation is an over approximation and the right hand is under. So it depends on the function which approximation gives over or which one gives an under approximation. But to actually find the exact area under the curve, we're going to have to formalize these definitions a little more. And here we have the formal definition for these approximations. Let f be defined on the closed interval a to b. Divide that interval into n subintervals of equal width, and we're going to call that equal width for simplicity delta x. Based on those previous computations we did, we saw that that delta x was the same as b minus a over n. But for this definition, we're just going to call that delta x. But for our computations, we will think of it as the length of the interval divided into n pieces. We're going to call those subintervals these subintervals here. More on that in a moment. Well, no, let's just talk about that now, I guess. Right here is just providing notation that allows us to count through the intervals. So here we have the first interval, the second interval, and the nth interval. It's just convenient for this notation to be able to count through those. But with that setup, we can formally define these two approximations. We're using n rectangles, so the left endpoint approximation with n rectangles is given by this sum. Notice it's the sum of n things. We're starting at 1, we're going to n. Well, all we're doing is length times width for each of these rectangles. Well, that's what we have here, length times width. This delta x, remember, is a piece on the x-axis. So that corresponds to this piece down here, the delta x. Now, f of x sub I minus 1, well, first of all, it's a function evaluated somewhere. So it's giving us other sides. And we just have to ensure that it gives us the sides we want. Well, with these subintervals, we want to use the left endpoint to define the rectangle. So let's see what happens when we substitute I equals 1. When we substitute I equals 1, you get f of x sub 1 minus 1. So that's f of x sub 0. F of x sub 0 is the function defined using the left endpoint here. Well, what if this starts at I equals 1? What's next? I equals 2. Well, when I equals 2, you get f of x sub 1. Because it's f of x sub 2 minus 1. So that gives you f of x sub 1. And again, times delta x to give you the rest of the rectangle. But right here, and if you go, let's go all the way up to the last number n, because we're adding from 1 to n. The last number n gives you f of x sub n minus 1. Well, f of x sub n minus 1 is the left endpoint on the last interval. So right here, this adds up areas of rectangles, because these are lengths times widths. It adds up n areas of rectangles. This is the left endpoint approximation, and we'll call that the left-hand approximation. And similarly, the right-hand approximation is length times widths, but they use right endpoints. And you'll notice they use right endpoints because, let's look at the first one and let's look at a couple of them. When you let I equal 1, you get f of x sub 1. X sub 1 is the right endpoint over there. You let I equal 2, you get f of x sub 2. That's the right endpoint there. You let I equal n, you get f of x sub n. So you get x sub n, the last right endpoint approximation. And remember, all of these approximations we're doing are ways to approximate on the interval a to b this exact area. So we're trying to find that exact area. We're using these approximations using rectangles, because rectangles are quite convenient shapes to find areas of. I mean, it's just length times width. That's a much easier area than any other shape, except maybe a line, if you consider a line a shape. What is the area of a line? Yes, it is 0. The area of a line is 0 because it's what? A one-dimensional thing. Area is a two-dimensional quantity. Lines have no one dimension, no other dimension. It's just like saying the volume of a plane, the volume of a flat plane, one of those, not a flying in the airplane. The volume of the plane, I think they usually call it that in a high school geometry class, is 0 because volume is a three-dimensional quantity. And planes have only area. But as a theorem, if we let n, the number of rectangles, go to infinity, then these two approximations actually give us the same number, and they give that exact area. So let's see how this computation works. Let's do the example we've been doing. Find the exact area under the curve, x squared plus, x squared plus 3 on the interval 1 to 3. Find the exact area. And when you have to find the exact area, then it's assumed you're going to use n rectangles and a limit. So example. Find this area. And I'll just draw it out because that's a little easier than writing everything out. So here we have f of x equals x squared. I'll draw it bigger. And I'll draw it on the next board because I'll do some of the algebra over here. This is f of x equals x squared plus 3. We're looking at the interval 1 to 3. We want this exact area. We'll call that A. The exact area, let's just label it A so we have a letter. A equals the limit as the number of rectangles goes to infinity. The sum of the rectangles. Now here, you could use the right endpoint or you could use the left endpoint. I find the right endpoint a little more notationally convenient to use. So I would recommend using only the right endpoint for this, just to remain consistent with a couple formulas we're going to use. But the area is the limit of a sum of n rectangles. Which rectangles? Well, we need a length and a width. Let's do the width first, or the... when I say length and width, I'm not really sure if I think of like this as the length or this as the length. When I think of rectangles, when you're finding the area, it's just one side times the other. So let's do this side first. Well, what's the length of that side? Well, we have an interval of length 2, and we're dividing it into n pieces. So we have 2 over n. We're using n rectangles. So the one side of the rectangle is 2 over n. Now what's the other side of the rectangle? Well, the other side is much harder to find notationally. Remember I said we're using right endpoints. So let's use the right endpoint. Meaning for this first interval, we need this value. We don't need 1, or what happens at 1, we need what happens over there. What's that? This arrow was supposed to have gone to the length of the interval. But now it's going to go to the next endpoint. So this x value. How do we get that x value? Well, we start at 1, and we move over 1 width of a rectangle. We start at 1, we move over 1 width of a rectangle, so that first one occurs at 1 plus 2 over n. The next one, you'll notice, to get to the next one, how do I want to write this? Let's write it like this. To get to the next endpoint, how do we get there? Well, we start at this one and we move over another 2 over n. So we start at 1 plus 2 over n, and we move over an additional 1 plus 2 over n. We start at 1 plus 2 over n, and we move over an additional 2 over n. In other words, we go over 2 over n twice. And we can use this sum notation to help us if we assume that we're using the right endpoints. So we use this 1 plus 2 over n, and then we let this I value, that's a lowercase I, we let that I value count out the number of 2 over n's we're going over. And we do that like this. Maybe I should have made it so it didn't go through the board. Well, whatever. We go over 2 over n, and we go over I times. So for the first one, we went over 1 time. For the second one, we go over 2 times, and so on. And we can now solve this limit. Now, how can we solve this limit? This limit looks pretty complicated. Well, there are a couple rules we're going to use in a moment. A couple rules that we'll see. But let's simplify it a little, because we know what f of x is. F of x is x squared plus 3. So let's just use this notation. 2 over n, and let's just deal with f of I, or f of 1 plus 2n over I. Let's just deal with f of 1 plus 2n. I said the same thing. F of 1 plus 2 over n times I. And we're going to write that here. But let's figure out what that is on the side. How far over on the side can we go? Let's go over here. F of x is x squared plus 3. So f of 1 f of 1 plus, I'm going to write that 2 over n times I as just 2i over n. I'm going to put that I in the numerator for now. If f of x is x squared plus 3, then f of 1 plus 2i over n is 1 plus 2i over n squared plus 3. Just replace all x's with that. Well, now we just have to square that out. We use that, a plus b squared thing. A plus b is a squared plus 2ab plus b squared. So we have 1 plus 4i squared over n squared. No, excuse me, I don't want to do that one first. I'll follow the order that is normally done. Plus 4i over n plus 4i squared over n squared, and then plus 3. So this right here is that square expanded. This is what? Is this thing squared plus 2 times this times that? Well, 2 times this times that is 1. So it's just 2 times this. 2 times this, 2 times 2 makes 4, and then the letters go along. And then this last thing squared is 2 squared, I squared over n squared. And then plus 3. And then this equals 4 plus 4i over n plus 4i squared over n squared. Adding the 1 and 3 together. So let's just write that down over here and see what happens. We needed f of 1 plus 2i over n, and we found it. 4 plus 4i over n plus 4i squared over n squared. Well, that's great. This limit does not look like it's getting easier. But it actually is. And it might become more obvious that it's getting easier if I give you 3 more relations, but I'm going to hold off on that for now. until we simplify this further. We still haven't taken a limit. We still haven't taken sums. Let's just distribute this 2 over n through. 2 over n times 4 is 8 over n. 2 over n times that next thing is 8i over n squared. 8i over n squared. Because we have an n here and an n there, so that makes an n squared on the bottom. We have a 2 and a 4i, that makes an 8i on top. And then the last thing, we have an 8. That's a terrible 8. Actually, it was a kind of cool 8. But it's a terrible 8 for recording purposes. Multiply the last thing, you get 2 times 4i squared, which is 8i squared, over n times n squared. So that gives us an n cubed. Well, that's great. Let's just look at this right now. Now, I'm going to skip one step in simplification. Well, let's look at this now. Some of you might be thinking, let's pull the 8 out. And you can pull the 8 out. That's fine. I'm actually going to not pull it out. But I am going to rewrite this at the top of the board. So this is just a rewriting of what was down there. That's an N, not an H. H is for the next lesson. So we have 8 over n plus 8i over n squared plus 8i squared over n cubed. Just rewriting this. Now to solve this, we're going to use 3 relations. Now you don't have to memorize these relations. If on a test I ask you something that would require these, I would write them on the side of the page. But I'm going to write them over here. Relations to use. 3 of them. The sum from I equals 1 to n of 1 equals n. The sum from I equals 1 to n of I is n times n plus 1 over 2. The sum from I equals 1 to n of I squared equals n times n plus 1 times 2n plus 1 over 6. Now you do not have to memorize these. I have, well, I have the first 2 kind of memorized. The first one's obvious once I explain it. This next one is a pretty important relation in math. This one is slightly less important, but it is still used, especially in this context. Now, what are these relations? Let's look at the first one. The sum from I equals 1 of 1. What does that mean? 1 plus 1 plus 1 plus 1. All the way up until you count out n times. So right here, we have n copies of 1. Add all them together, you get n. If you have 4 copies of 1, 1 plus 1 plus 1 plus 1 is 4. If you have 12 copies of 1, 1 plus 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 1 is 12. I think I counted out 12. 12 is kind of a big number to count to. But that's if you add 1 together n times. What about this next one? This says the sum of I from 1 to n is n times n plus 1 over 2. Well, this one down here would be 1 plus 2 plus 3 plus 4 plus all the way up to until you get to n. So 1 plus 2 plus 3 plus 4 plus 5, let n equal 5. Well, 1 plus 2 plus 3 plus 4 plus 5 is 15. If you let n equal 5 in this formula, you get 5 times 6 over 2. 30 over 2 is 15. And this last one is the sum of squares. So instead of 1 plus 2 plus 3 plus 4, this one would be like 1 plus 4 plus 9 plus 16 plus 25 until you get to n squared. And that has a similar formula. Now, how are we going to use these? We're going to use these to eliminate i's. And we're going to use these to eliminate sums. we're not going to use it to eliminate limits. But we are going to use it to eliminate the sums and the i's. So first, this is the sum. We're not going to talk much about properties of these big sums with sigma notation. But you can, for finite numbers, do them piece by piece. So you can do the sum of 8 over n plus the sum of 8i over n plus the sum of that last one. And what does that look like here? Well, this, remember, is 8 over n is 8 over n times 1. 8 over n times 1, well, we know the sum of 1 is n. So the sum of 8 over n times 1 is 8 over n times n. I'm not going to write that times like that. I think that dot doesn't look that good there. 8 over n times n. So that gives us this first piece. What about the next piece? Well, there's a plus sign connecting them. 8 over n squared is next. Times I. So remember, 8i over n squared is 8 over n squared times I. And the sum of I is given by this formula. The sum of I is given by that formula. Well, and then this last piece has I squareds on it. So we're going to pull out 8 over n cubed. If you pull out an 8 over n cubed, you have 8 over n cubed times I squared. Well, this formula here gives us the sum of I squared. We have 8 over n cubed times I squared. We need to multiply it by the sum of I squareds. And now that I'm at the end of this board, I'm going to erase this because we'll be done using these relations. So if you need them on a test for this type of context, I would write these relations on the side. But you do need to know how to use them. So this is what? N times n plus 1 times 2n plus 1 all over 6. And we started a parenthesis, so we should end the parentheses. So now how do we do this limit? Well, this is actually a limit we've seen. In the previous video, we know how to take this limit. But before taking it, let's just simplify a little. This first one is just 8. The next one, how do we want to do this? Let's pull out the 8 and the 2. 8 and 2 make 4. And you're left with n times n plus 1 over n squared. So I combined the numbers, and I left the n's alone. And over here, we'll do the same thing. 8 and 6 make 4 thirds. N plus 1, 2n plus 1, all over n cubed. We'll leave those alone. We still haven't taken a limit, but now we will. And we're going to use an observation I made in the previous video about coefficients. When you have a rational function, you look at the coefficients on the largest degreed term. So if you're asked just to do the limit, you have to go through the details, and the directions will say that. Something like that. If you have one of these where we're finding the exact area, we could just, well, I will allow that you can just look at the coefficients. Coefficients here, well, there are no n's there, so the limit is just 8. The limit here is 4. And what's the coefficient on n? What's the coefficient on n squared? The bottom has degree n squared. The top has degree, the bottom has degree 2. The top has degree 2. The coefficients on the n squared term on top is 1. The coefficient on the n squared term on the bottom is 1. And how about this last one? Well, the 4 thirds carries on through. In the bottom, we have degree 3. In the top, we have degree 3. And these will be set up so that the degrees on top do equal the degree on the bottom. That's a result of those formulas. The bottom has degree 3. The coefficient on n cubed is 1. The top has degree 3. The coefficient on n cubed is 2. Because it's 1 times 2. And now we just add all these numbers. 8 plus 4 plus 8 thirds equals what? 12 plus 8 thirds? So that's 14 and 2/3. I'll use the mixed number here. So we get 14 and 2/3 is this exact area. And you can check, with all those approximations we did, the left, this gave us the exact area between 1 and 3 on the function x squared plus 3. This gives us the exact area. This tells us the area is 14 and 2/3 of whatever our units are. All of the left approximations we did, the number was less than 14 and 2/3. All of the right approximations we did, the approximation was more than 14 and 2/3. So there's one of these on the worksheet. Try to see how this goes, setting up this limit. Setting up the limit is a lot of the work.